we are doing B plus trees, and as we mentioned earlier, B plus tree is the balanced binary search tree which has got operations insert, delete and find, all of which can be done in order log n time, where n is the number of distinct index values or attribute values on which the indexing is done. There are two types of nodes, a leaf and an internal node. All leaf nodes are at the same depth in a B plus tree, and each node is the size of a block, and for an internal node, each node is always half full, that is the number of pointers that it has, at least half of them must point to valid nodes and be non-null. We have also seen the how find operation goes on in a binary search or a multi-way search manner, doing it in log n time. We have also seen the simplified insert operation. There are more complex insert operations which does compaction, but as has been mentioned by somebody here, that compaction may or may not be useful in many cases, because if we compact, we may have to generate newer nodes. If we compact every time, we not only spend time in compaction, but we spend time during insertion, extra time during insertion as well. It is just that if we compact, we reduce the height of the tree and it increases our efficiency of find. So it's a two-way issue, and maybe depending on if you have some ideas regarding the data distribution, then something may be done. Now finally we will see how we do the delete function. Let us see, say we have a B plus tree like this. If we have to delete 15, we go here, delete 15, make this null, make this 10, finished. This is the root. If we have to delete 15, any delete function is first find it. If it is not there, delete does not work. If it is there, then come here. If there is only, if it is the only value which is present here, then delete it. If this is non-empty, then just update its parent and go on updating. Similarly, delete 25. If we delete 25, we push 30 here and update. Here nothing is to be updated, and this remains as it is. If we delete 20, then we have to do some more things. If we delete 20, we will have to put this pointer here. So the first thing that we have to do if we delete 20, this pointer comes here, this is removed, this points here, and this is made null, and this value is updated to become 30. So on a delete 20 operation, how will you get this one? From the parent, you just move to this side, you will get this pointer, or pointer to this node. This pointer dot next now points to this pointer dot next. So if you want, for purposes of easy programming, maybe you can keep parent pointers as well, and you can keep previous and next as well. It is not essential to maintain the order and complexity, it may just help in programming. That is, when you do this, you sometimes see that your record and block sizes are such that you have a lot of space which you can use. If you have some additional space which you can use, then you can do many things. Even at the internal nodes, you can maintain the brothers. It depends on the ratio of the block size and the record size, and if you really have some space, then you can put the previous, the next, the parent, the child. But if you don't, then this is sufficient to maintain the order of n complexity by just modifying your algorithm a little. So delete 20 will lead to a structure which is 15, 30, I'm sorry, This was the structure, now this will be the structure when you delete 20. Now suppose here you delete 15, it's fine, this will become 10. So if you delete 15 here, this will become 10. If you delete 10 and 15 both, then if you delete 10 and 15 both, then this one has got only one pointer. Now this is not allowed. There is only one leaf node, so you need not have any root, this will become the root. Let us see this in slightly more details. Suppose you have a structure like this, and at this point of time, if I delete 15 it is okay, but if I delete 20, if I delete 20, I will come here, search 20, find that 20 is null, 20 is deleted, then this record becomes empty. Once this record becomes empty, I will throw this away and I will ground this, and I will delete this one from here. So when I delete this one, this pointer, when I delete from here, this will have only one pointer. Once this has got only one pointer, then this is not a valid node. This is not a valid node. So we have come to a situation where a node has got only one pointer, then such a thing is not allowed in a B plus tree with 3 pointers. You cannot have only one pointer and 2 null. That is, this one cannot be made null, then this will not remain a valid B plus tree. In such a situation, you check whether this is root or not. If it is root, then just throw it away and make its only child the root. In this special scenario, this is the root, just throw it away and make its only child the root, and after delete of 20, we will have a structure like this. So the operations are find 20, delete it from here. If this leaf record becomes null, then update the pointer. Suppose this had something else pointing to it next also, you would have had to update it. We will see that case also. So update that. In this case, this will be null. Delete this node, the pointer to this node in the parent. Once I delete the pointer to this node in the parent, check whether this internal node violates the condition of the B plus tree, and if it does, then there are two cases. One is check whether it is root. If it is root, just throw it away and make its only child the root. If it is not the root, then we have to do something else, which we shall see in another example. Let us take this case. We have got 10, 15, 20, 25, 30, 35. Here it is 15, here it is 20, here it is 30, here it is 35, here 20 is the largest, here 35 is the largest. So this is a valid B plus tree. If I delete 30, then there is no problem. I will just remove this, I will make this 25. If I delete 30 or if I delete 15, I will make this 10, and there is no problem. But if I delete 20 or if I delete 35, I will end up in a bigger problem. If I delete 20, let us see what happens. This is deleted. When I delete 20, this becomes null. So I will have to throw it away. Before throwing it away, I will have to update this pointer. Then I will have to delete this. When I have deleted this, I will check whether this node violates the condition of a B plus tree. It does. Then I will check whether this is root. It is not. In that situation, I will have to go and delete it from here. But before deleting it from here, I will see it with its neighborhood or brothers. I will see its situation with its brother. Here, its brother is not full. So its brother is not full. So what I can do is, I can push this 15 here. So I have come to a situation, I have deleted this. I know how to delete a leaf node. If a leaf node is null, I go and delete that node, change this pointer, and then delete the pointer at the internal node. Now coming to an internal node, if I see that after deletion of the pointer at any internal node, be it here, 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 anywhere, if I see that after deletion of the pointer, the node does not violate the B plus tree condition, I just propagate and update the values of the attributes along the tree, I do nothing else. But if it does violate the condition, then I have to do an adjustment. What is the adjustment that I have to do? I have to now adjust it with its brothers. If its brothers are not full, there is only one element here, one pointer. If its brother is full, then it has got 3 pointers and this has got 1. I will bring 1 pointer from here and put it here. So there may be, with its brothers, with its just next brother, there may be 2 cases. Case 1, this has got, node has got 1, the brother has got 3. Then I will redistribute. Which is not the case here. If it were the case here that this had got some other pointer, then I would have been able to redistribute this thing here and maintain the tree and balanced it up. The case 2, 1 and 2. Then what do you do? Redistribute it to be 0, 3 and delete the 0. Redistribute it to be 0, 3 and delete the 0. So let us see it step by step. So after we have deleted this, this is not there. We will shift this here and we will get a structure like this. The structure that we are drawing now is a partial state. It is not a full state after the complete deletion. It is a state in which deletion is being done. We have redistributed. We had 2 here. We distributed this and made this have 3 pointers. We made this have 3 pointers pointing 1 to here, 1 to here and 1 to here. So we have got only 1 node here. So we will have an intermediate structure like this, and this value will be 15, this value will be 30. And we also had its parent who was existing like this. We have deleted this and we had its parent. And now once we delete this node on the parent, after updating this like this, we delete this node on the parent, we see that now this node dissatisfies the condition of an internal node, because there are two pointers which are null and it is a root node. It is a root node and it dissatisfies the condition of an internal node. Then we have a simplified solution here. We make its only child the root and we just throw this node away. So what we now have is this structure. We had 20 here, we deleted it, we found that this was having a node like this, we deleted it, then we redistributed it, and then we found this violated the condition, we deleted it, and we got a situation like this. Let us see another example which is a slightly simpler one. Let us see this. Suppose we delete 25. If we delete 25, in a leaf node, we will remove it. If it is null, then this will be done. We will delete this. This violates the principle. Once this violates the principle, we will try to redistribute it this side or this side, whichever. Any one policy will do. This side is null, so redistribute it this side. When we redistribute it this side, we find that this is null. So a simple solution is make this point here, because the 30 will come just after this, and delete this. When you come to delete this, we find that this violates the condition. Once this violates the condition, then it is a root node. Since this is a root node, there are two cases. If it is not a root node, then you redistribute. If it is a root node, then just make its only child the root and delete this. And we will have this structure 15, 20, 10, 15, 20, 28, 30, round, root. So deletion is fine, and there are cases of delete leaf if required, and delete internal node if required. For a delete of a leaf node, if it is null, you just delete it, change the pointers and delete the pointer from the parent. Now, when you come to an internal node and you find that it does not, if it satisfies, still satisfies the condition, then it is all right. If it does not satisfy the condition, see two cases. The first case is if it is root, then just make its only child the new root and delete it. If it is not the root, then redistribute it with its brothers. And the brothers, there will be two cases, 1 3 and 1 2. 1 3 means redistributed 2 2, it becomes a simple situation. If it is 1 2, then make it 0 3, remove that internal node and then go to its parent again and remove that pointer from its parent and recursively proceed till you reach the root. This is the idea of a B plus tree. Now, there are various other structures, of which the B tree is a more complex variant of the B plus tree. Before that, the algorithms which we have discussed here are very simple, in the sense that we allow a leaf node to contain only one value. Even if a leaf node can contain 25 records, we will allow it to contain one value only by our algorithm. Some other people may decide that when you delete this 25, you try and see whether you can compact the elements from this side or compact the elements from this side and do a recompaction. So, there are algorithms which try to do various techniques of compaction, and they will be intricate in their own way, and each will have a variant of the insert and delete functions. A B tree, unlike a B plus tree, is like this. It tries to save space in the following way. For an internal node, say this is the internal node of a B plus tree, of a B tree. In a B plus tree, this side we contain leaf nodes pointing to less than equal to 20, this side leaf nodes greater than 20 and less than equal to 30, and this side greater than 30. In a B plus tree, here will be strictly less than 20, here will be greater than 20 and less than 30, and here will be greater than 30. Now, what about the elements pointed by 20 and 30? They have special pointers here. This is the element equal to 20 and this is the element equal to 20. So, instead of going right down to the leaf node, at an internal node, if you have a value equal to the key field, from that internal node you get a block pointer. If it is not equal, less than this side, greater than and less than this side. If it is equal to 30, you have a direct block pointer. Therefore, there may be, all the nodes will not be stored only at the leaves in a B tree, they will be stored at various places. Only those which are not equal to these values will be stored down the search tree. This is similar to the concept of a binary search tree, where you see whether the value exists at the node. If it is at the node, then you have found it. If it is not at the node, then you check the left. If it is less, you check the right if it is greater. Here, if it is at the node, then you have found it. Otherwise, you go to any of the pointers. Here, if it is 20 or 30, you will have got it. Otherwise, so here the insertion, the find and the delete operations will be slightly different from what we have in a B plus tree. Here they will make use of this additional effect. This tries to reduce the total height of the tree because it stores some internal nodes. It reduces the find time also, but the insert and delete will be slightly more complicated than which we have in the simple B plus tree. There are other types of file structures. of which hashing is a very popular technique which is used for indexing, which is known as hashed index. We remember that hashing is a function from an attribute to a value, and we will try to have a numeric function which tries to work on this attribute and compute a block value, and we will our insertion operation will use this function and compute the block value based on the attribute and then search sequentially in that block. Our delete, insert and find, all operations will use a function which will be computed on the main memory. It will look at the attribute, compute that function and generate a block. Now, the more unique we are able to make this function and the more well distributed we are able to make this function, the better hashing that we will get. It is similar to the hashing technique which you use in normal data structures. As we have seen, all these techniques are useful as they are useful in the normal data structuring, but we have to make it amenable to the disk structure. We have to properly utilize the concept of blocks because we know that only block accesses are done. I will not go into details of an hashed index, but I will expect that you will just be able to read it up, or you will be able to develop it from the standard hashing techniques which are available based on the idea that the value of the hash function will give you the block address rather than the key actual record pointer. So, we will not discuss hashed indexes, but I would expect that these hashing function or hash indexing is studied in details from any standard